I'm excited to be here today to present our work titled ESCNet, Edge-Semantic Collaborative Network for Camouflaged Object Detection. In this presentation, I'll walk you through the challenges that motivated us and the novel framework we developed to address them. Here is the agenda for my talk. I'll begin by setting the stage with some background on camouflaged object detection and the limitations we identified in prior work. Then, I'll detail the core contributions of our paper. After that, I'll dive into the specifics of our methodology, explaining how our ESCNet works. We'll then look at the extensive experiments we conducted to validate our approach. And finally, I'll summarize our findings. So let's start with the problem we're tackling: camouflaged object detection. The goal here is to segment objects that are masterfully hidden in their environment. As you can see, this is incredibly difficult. The objects share almost identical textures and colors with the background, and their boundaries are often ill-defined. This challenge is not just an academic curiosity. It has critical applications in areas like medical diagnostics, biodiversity monitoring, and even industrial inspection. When we started this research, we analyzed existing methods and identified several key limitations that were holding the field back. We found that most approaches, by relying on a single type of feature, often produced incomplete predictions. We pinpointed three core problems. First, the fixed receptive fields of standard convolutions are simply not suited for the irregular shapes of camouflaged objects. Second, edge and texture analysis were often treated as separate tasks, which is a missed opportunity for synergy. And third, we saw a lack of mechanisms to ensure edge and texture features were consistent across multiple scales. To address these limitations, we propose ESCNet. The core idea behind our work is to create a dynamic and synergistic coupling between edge and texture perception. Our framework is built on three core innovations that we designed. First, our AETP module, which establishes a symbiotic relationship between edge and texture cues. Second, our DSFA module, which intelligently enhances features at object boundaries. And third, our MFM module, which performs hierarchical fine-grained refinement. Together, these components create a self-reinforcing feedback loop, which is the main contribution of our work. Now, let me walk you through the overall architecture of our ESCNet. We designed it with a classic encoder-decoder structure. For the encoder, we chose a Pyramid Vision Transformer, or PVT, because it's highly effective at extracting rich, multi-scale features. The decoder is where the magic happens. It's the heart of our work and contains the three custom modules I just mentioned: AETP, DSFA, and MFM. Here, we progressively refine the features in a collaborative manner to generate our final highly accurate segmentation. The first key module we designed is the AETP. We developed it to act as a relationship builder between edges and textures. Its primary goal in our framework is to produce a high-quality initial edge map. To do this, we designed it to combine multi-scale features with global context, so that the model is forced to consider surrounding texture information when predicting an edge. This makes our initial edge map much more robust and less prone to ambiguity. Once our AETP generates the initial edge map, our DSFA module takes over. We designed this module specifically to act as a feature enhancer for ambiguous boundaries. We leveraged deformable convolution as its key component. What's novel here is that in our design, the sampling offsets of the convolution are guided by the edge map we just generated. This allows our model to focus its computational power exactly where it's needed most, on the object's true contour, leading to a far more precise feature representation. The final piece of our framework is the MFMM, which we designed to be a prediction refiner. This module in our decoder works in a coarse-to-fine manner. At each stage, we designed it to consider not only the current features, but also three crucial priors: the mask from the previous stage, our global edge map, and texture details from a Laplacian prior. By fusing this information with a novel attention mechanism, our model progressively polishes the prediction, ensuring the final output is highly accurate. Now for our quantitative results. As this table shows, our model, ESCNet, achieves new state-of-the-art results on all three datasets. We were pleased to see that it outperforms competing methods on the vast majority of metrics, often by a significant margin in most cases. This strongly validates the power of our proposed Edge Texture Collaborative Framework. Beyond the numbers, we believe the visual results are also very compelling. In these difficult cases, you can see that other methods struggle, producing fragmented or incomplete masks. In the Rs column, you can see that our model consistently produces segmentations that are more complete, with much cleaner and more accurate boundaries. This really highlights our model's robustness in the wild.
To verify that each part of our design was contributing, we conducted a thorough ablation study. We started with a simple baseline, and then incrementally added each of our proposed modules. The results were very clear. Each component, MFMM, AETP, and DSFA, provides a significant and cumulative boost in performance. This confirmed for us that all three modules are essential and work together synergistically to achieve our final results. In addition, we also conducted ablation studies on the individual components of the MFMM module, with the results shown in the figure below.
To conclude, in this work we introduced ESCNet, a novel framework for camouflaged object detection. Our model's core strength lies in its ability to create a dynamic, self-reinforcing collaboration between edge and texture perception. Through our three innovative modules, we have been able to set a new state-of-the-art on three challenging benchmarks. We believe this work not only pushes the boundaries of COD, but also offers a valuable paradigm for other segmentation tasks where ambiguous boundaries are a key challenge.